Seems weird to record a review, but I have had a request, so we are now recording the review. All right, so the superposition laws are the things where you have contributions from many individual sources and they're all contributing. And the total field that is the solution to the problem is the sum of all of the individual contributions from each of the smaller sources. I noticed on the midterm that a lot of people had issues with the charge distribution. I wasn't sure if it's just that you assumed that every charge distribution problem is a surface charge problem, but I want you to remember that there are line charge distributions, surface charge distributions, and volume charge distributions. A line charge is distributed along a one-dimensional curve or line or something. A surface charge distribution is distributed over a surface, and a volume charge distribution exists within a volume. Any one of these things can depend on position. They may or may not be constant. All right, so after we did the superposition laws, the next thing we did was flux laws. We spent a lot of time in that chapter finding the electric field and the electric flux density due to a charge distribution with symmetry. Using Gauss's law. No, we're not doing a screenshot participation assignment today. We also defined magnetic flux. Those were the things that happened in chapter 3. Then we did some other stuff. I guess we also defined inductance here. Even though inductance is the inductance equation, V equals L di dt is a consequence of Faraday's law. We defined inductance in this chapter before we talked about Faraday's law because we defined the magnetic flux here. And inductance is like the inductance of a structure is defined as the flux or the flux linkage if there are multiple loops divided by the current. So that's what happened in chapter 3. Then, in chapter 4, we did the path laws. But only in static form. So this was Ampere's circuit law and finding the magnetic field from it. We also talked about Kirchhoff's voltage law and the definition of voltage. Then things started to get really interesting after chapter 4 because we started doing time varying stuff. Right? In chapter 5, we did Maxwell's equations. That was the title of the chapter, but it included things like Faraday's law. So ideas like the EMF, we talked about electric motors and generators in there. We also talked about Ampere's law with displacement current. And then with those two things together, we introduced plane waves. Now these show up later in your book. They're not part of chapter 5, but I put them in chapter 5 because once you have Maxwell's equations, plane waves naturally fall out, and I think they're one of the biggest impacts of having the dynamic forms of Faraday's law and Ampere's law. So I put them here. The place where they really show up in the book is chapter 8 when we're talking about antennas. Then, let's see, after that we had chapters 6 and 7 about transmission lines. Chapter 6 had transmission lines kind of at DC. So we talked about reflection, mostly reflection. And then we introduced transmission lines for time harmonic stuff. And the reflection coefficient here was in chapter 6. And then chapter 7, we talked about transmission lines for time harmonic stuff. So that got you the input impedance Smith charts. Power on transmission lines, I think we talked about in chapter 7. We talked about return loss and insertion loss. And then we had chapter 8, antennas. We talked about plane waves again. We talked about the pointing vector. We talked about antenna metrics, so like gain, directivity, efficiency, and polarization. And then lastly, we talked about the Friis transmission formula. And that was last week. This week we talked about signal integrity. That was more of an informative lecture than a thing that is actually going to be on the test. I want you to be aware of those topics, but there wasn't a lot of things I can really assign a problem about. there might be a small conceptual question on that stuff, but not like a big problem. So 9 sig integrity. And that's that. So I'm going to give you a minute to think about it. And I would like some suggestions for what topics would you like to review? Do you have questions on? Do you want to see an example problem? Do you want to get in small groups and work through a problem of a particular kind together? What do you want to do? Let me know.
So I just have like, I guess a more general question, because I think for the most part, a lot of us have trouble with electromagnetic dynamics or the dynamics section of um, fields and waves, which is just Maxwell's equations. Um, Most of us have trouble with setting up the integral for a very like specific problem. Like for the most part, we know that most of the problems have like some homogeneous charge distribution or a uniform charge distribution function. And but it all boils down to finding uh, an expression for the differential surface area, for example. I think most of it boils down to that. So the textbook kind of oversimplifies like a lot of the processes of simplifying the differential surface area. I'm just wondering, like, how do we ascertain the differential surface area or the expression for the differential surface area?
It depends what your surface is shaped like. In general, and I think this doesn't just apply to dynamics problems. This applies to any time you have to do an integral, which is all of chapters 2 through 5, really. It's not just the Maxwell's equations section. In that one, it comes up in some of the Faraday's law stuff, though. Yeah, I think the way I would do it, if I had some surface, it might be a weird surface, but let's say that it is parameterized by 2 variables. So I'm going to try to draw a grid on this surface that is not especially regular, like this maybe. But I have 2 variables that describe this surface. And for the sake of argument, and to make this really general, I'm going to make them U and V. And I need to come up with, when I'm finding that differential surface area, I need to come up with what is the general expression for the area of one of these squares. If I move one differential length along U, du, and I move another differential length along V, dV, how long is that length? So then my differential surface area, I could write it, in fact, as like, if I have a u-directed unit vector, a hat u du cross a hat v dv is my surface normal differential surface element. But what's the length of du? What's the length of dv? That depends on how exactly the surface is parameterized and how it is shaped. So let's talk about some specific surfaces, because I think that having this framework in mind when you get into a specific example will really help. Consider a circle. Let's say we have a circle here. I'm going to say we are in cylindrical coordinates. So I'm still drawing my Cartesian coordinate axes. You know, here's x And here's why, but I'm doing that because my angle phi is defined. Can I zoom out anymore? Not really. I'm doing that because my angle phi is defined relative to the x-axis. And rho is defined relative to the origin in the xy plane. So if I wanted to integrate something over the area of this circle, my differential surface element, actually that's okay, would be, I would have to, let's say we're talking about this little section right there. I would need to know the length of this side and the length of this side or this side. Technically, they're slightly different, but if we're working with differential sizes, it is not important that they're slightly different. So the length of this side, the radial distance from the center is rho. So I'm moving from rho equals this value to rho equals that value. So that distance is just d rho. That one makes sense. But what about the length of this side, the one that varies along phi? Phi is not, it doesn't have dimension of length. It's not a length variable, it's an angle variable. So these two lengths, although they are physically different, both sweep through an angle of d phi. On the other hand, the length of this side can be specified as the arc length, rho d phi. And that is a fact that you have to know about circles, that if you want to know the length of an arc of a circle, it is the angle that's being swept through times the radius. So my differential surface element here, if I use the formula that I just wrote down on my more general example, I would have to do a hat rho d rho cross a hat phi rho d phi. And in fact, when I do that, I get a hat z rho d phi, which is a differential surface element for a circle in cylindrical coordinates. Does that make sense? Want me to do another one?
Yeah, this one makes sense to me. I think the one that gave me a lot of trouble was the example where like there was like a rectangle spinning um on the z-axis, and it was spinning in the a hat phi direction, and then there was a constant magnetic field directed x. I'm not sure
Okay, I
exactly.
think I know what you mean. That was a sort of an electric motor problem. So let me draw that and make sure that I've got it correctly. I'm going to draw two views of this thing because that I think will help. So here's my coordinate system, x, y, z. Made that a little extra tall there. Okay. And let's say that I have a loop that is centered on the z-axis. It is square and it has side A. And it's rotating in the plus phi direction, like that and like that. So right-handedly around the z-axis. That would be counterclockwise if you're looking down at it. If I am looking down at it, I can also draw it in the XY plane. There's X, there's Y. Here's my loop, and it's sort of moving that way, in that direction. And it has a particular speed that it goes. We give it an angular frequency. So we get a angular frequency omega, where omega t equals the angle that this thing is at as a function of time, that like this point is at. I'll leave that there. So there's two different ways to think about this problem. You can think about it as the loop is moving and did you say the magnetic field was X directed or Y directed?
I said it was X directed, but I'm not sure what the original problem was.
Okay, well we'll just go with what you said. All right, so we have a magnetic field here that is X directed. And there, it exists everywhere like this. There are two different ways to solve this problem. One way, you can assume that you're working from the point of view of the field and the loop is moving. Or you can assume that you're working from the point of view of the loop and the field is moving. The field is changing direction as time advances, but the loop is holding still. I like to think of it as the field is not moving and the loop is moving. So the way that I'm going to do that is I'm going to write that the magnetic field is some amplitude a hat x, and that stays the same all the time. With the loop, I'm going to define, I'm doing this really, really explicitly, and normally I would skip some steps in my head, but I want you to be aware of what the steps are that I'm skipping. Okay, so for the loop, I'm actually going to effectively define a coordinate system that is local to the loop. So here's my loop. And I'm going to give it like a U and V coordinate system. And on the loop, the magnitude of ds is du dv. And u and v work exactly like x and y, except for one important difference. And that is that a hat v equals a hat y. Is that true? No. V is z actually, not y. I was wrong. So v is coming out of the board, and u is going to change direction as the loop turns. All right. So a hat v equals a hat z. A hat u, on the other hand, is equal to, let's see, when t equals 0, I'm going to say that it's along the x-axis. So that means a hat x cosine of omega t plus a hat y sine of omega t. So now I have this time-dependent unit vectors that are defined in this coordinate system. When I figure out the unit vector direction that applies to ds, I cross a hat v and a hat u, but I'd like to express it in the stationary coordinate system, the one that is the one in which the field is not changing. So I'm going to have a hat v cross, I'm going to do u cross v. It doesn't super matter, but I'm going to do a hat u cross a hat v. So that would be ax cross az is going to be minus a hat y cosine of omega t, and a hat y cross a hat z is going to be plus a hat x sine of omega t. Sorry, you can't see it down there in the corner. So now I have a time varying ds, which is magnitude given by du dv, and direction given by a hat x sine omega t minus a hat y cosine omega t. Okay, cool. Now we're in business, because what we have to do is figure out, now we have to figure out the magnetic flux through the loop and its time derivative. Does this make sense? I don't think this, I think I evaluated this wrong or something, because that should be, I drew this wrong. This is a y-directed magnetic field. That's the problem. I'm just going to write down a hat y because I like this diagram. I was like, these dot products are not going to work out right. But it's because I drew this along y and just said it was along x. And that is honestly an easy mistake to make. Okay, so we're ready to do it. I'm going to go up here into the top left. The magnetic flux here is equal to the integral over the loop. So like along u and v of h naught a hat y dot, oh, and it's b dot ds, so I gotta put mu in there, dot a hat x sine omega t minus a hat y cosine omega t du dv. Nothing inside this integral depends on u or v. So we end up just multiplying by the area of the loop, because we integrate along u and get a factor of a. We integrate along v and get a factor of a. When we evaluate this dot product, a hat y selects out the y component of our time varying surface normal vector. And what we end up with is that the flux through the loop is mu naught h naught minus sine cosine of omega t. Questions about this so far? We did a lot just now.
For this specific integration, would the limits just be from negative u to u? Because, oh wait, actually no, it'll just be, okay.
Those are A's on the top. Sorry, went off the screen there. It would be like that. Remember, u and v are variables. They work exactly like x and y work. It's like we just made a different xy plane. Or I keep forgetting v is actually z directed, right? So here are u and v And it's just that this particular instance of our xz plane is rotating. So I could have named these x prime and z prime if I wanted to. Or I could have named them alpha and beta. But whatever they are a coordinate system. And they are going to be the variables of integration for over here. And they're going to go from some constant value, in this case I defined it to be 0 at the bottom left corner, to a. And then you get that. So then if you were doing a Faraday's law problem and you wanted to know, right, you wanted to know the induced EMF because of this, it would be minus the time derivative of the flux, which would give you, is the derivative of cosine a sine or a negative sine? Negative sine. So minus mu naught h naught omega times sine of omega t will get you your induced EMF. How do you feel about that? So far, so good? Let's integrate something over a spherical volume next. You want to do a charge distribution Coulomb's law problem?
Yes, but I'm sorry, before you erase it, could you just go over where the A's went in that? The limits of integration?
Oh, you're absolutely right. I forgot to write down the A's that are here and the A's that are here. Thank you so much.
Okay.
I
Because
kind of told you about evaluating them and then I didn't evaluate them. I should know
they're
better.
the
I
only
haven't had
thing,
coffee.
and they're the only things that gets evaluated. The rest of the parts of the equation are really dependent upon them and can come out.
Right. Nothing else in here depends on u and v. So when you evaluate du and dv over these bounds, you just get a and another a.
I thought I really misunderstood for a second, but
Sorry about that.
no, thank you. That did help a lot.
That's the consequence of doing a review session where you get to make up the problems, is I haven't prepared them, so I'm going to make mistakes. So I appreciate it if you catch them. Okay. I was going to suggest a volume. Are we ready to do that, or any more questions about this one? Okay. Volume charge density it is. I think we should try to do the same problem two ways. So we're going to do a problem that can be done either using Gauss's law or using Coulomb's law. Oh, actually, this integration stuff is important, but since we've talked about it a little bit, I don't want to spend all my time on that because I just remembered another thing that is really crucial to go over. I think people are having a lot of trouble with 3 different types of integration surfaces that we define when we're doing different types of problems, and when we use each one and how we should do it. All right. There is the Gaussian surface. There is the Amperian contour. It has an associated surface too, but we usually talk about defining the contour. And there is the flux surface. for like inductance problems. These have a lot of things in common and a lot of things that are different. The Gaussian surface and the flux surface are both surfaces. The Gaussian surface should have the electric flux density perpendicular to the surface or parallel to the surface or zero. The flux surface, oh, and the Gaussian surface is closed. And if it doesn't surround a non-zero net charge, you will get zero for your electric flux density. On the other hand, the flux surface, when we're trying to calculate the magnetic flux, that should be open because the divergence of the magnetic flux density is zero. So if you try to calculate the flux out of a closed surface of a magnetic field, you will get zero because of this. But it should be perpendicular to B. For some reason, I thought it was parallel the dA. I need a little bit more specificity there. Are you saying that you thought that the magnetic field for a flux surface should be parallel to the differential area? That's the same as being perpendicular to the surface because the dA vector is always perpendicular to the surface. That's part of how you define the dA vector. It's a property of that vector. So the surface should be perpendicular to the magnetic field so that your magnetic field actually goes through it. This is the sort of thing you want to see down here in the bottom right corner. That's what you want to have happening when you're doing a flux surface. Gaussian surfaces are also flux surfaces. They just happen to be closed. This is a flux integral, electric flux density right there. And this is also a flux integral, magnetic flux density B. Flux integrals, in general, you want the field to be going through the surface. If the field is not going through the surface, if the field's vector direction is not perpendicular to the surface, you will get zero for your flux integral. That's no good. Okay, so those two things have that in common. Both a flux integral, also a flux integral. On the other hand, the Amperian contour, not a flux integral, it's a contour integral, right? We're going to do integral of h dot dl. So what you want is the contour. I'm going to write it as partial s. That's the contour. S is the surface that's bounded by the contour. I need to make room on my whiteboard. And these two things both have some specific properties. One, the contour should be parallel to H or perpendicular to H or H equals 0 on the place where the contour exists. Second, that surface, you need to be able to evaluate the amount of current flowing through the surface. It's not that the current needs to be perpendicular to the surface. It's not that the current needs to be constant over the surface, but this has to be an integral you can solve. Any questions about Amperian contours?
I guess defining the path for DL was a little confusing to me. The path that the current, I mean, it defines an area that the current sort of pierces.
Yeah, it's as though you are defining some area, and like this is DL, right, along here. The current is coming into or out of the board. I'm going to say it's coming out. That's the current. And you want your magnetic field to be sort of parallel to DL. That's J in there. So the contour should make a circle around, no, not necessarily a circle, but often a circle around J. I want to give you an example. It's a midterm problem that a lot of people had trouble with. So I want to just point out the way to do this while we're talking about it. Think about a coax cable. I will draw an end view and a side view. If I have current flowing on the inner conductor this way and the outer conductor this way, you know, in this one it's out of the board here and sort of into the board on the outer conductor. It's not in one place, it's evenly distributed around. My Amperian contour should be the one that goes around one of these currents. So my Amperian contour might be, or really should be, a circle of variable radius, make it rho, that encircles this inner conductor current. And that's for doing Ampere's law. So H dot dl equals the current flowing through there. And I need to give this contour a direction. And then I need to make sure that that's consistent with the direction that ds points. Because I need to have this dl, the direction of the contour, be right-hand rule-wise oriented to the direction of this surface normal vector. So in this case, since I've defined the contour to be counterclockwise like this, the surface normal vector should be out of the board. That's for this part of the problem. That is how you find the magnetic field. But when you want to know the flux, when you're trying to figure out the inductance per unit length of this structure, you don't use the same area here. You don't use that same surface. Because this surface is parallel to H. So there's no flux. We don't like that. We're going to use a surface that is not parallel to H. The magnetic field in this thing circulates around the current. Remember the grab the wire trick? Never actually grabbed the wire, but that's how the magnetic field is going to be going. So I'm going to have a magnetic field that is, grab the wire again, coming out of the board here and going into the board here and sort of circulating around this center conductor in the plane of the board. Man, it's hard to draw in 3D. So if I want to know the inductance per unit length of this structure, my flux surface is actually going to be this. Because that is the surface through which flux exists. In general, for a flux surface, you want the flux surface to be perpendicular to the flux density you're integrating. And for inductance, you want the current to go around the flux surface. And here it does. The current goes this way and then it goes this way. This loop of current is being linked by that magnetic flux. Any questions about that? If I gave you a different transmission line, would you be able to figure out how the flux surface should generally be sort of parallel to the current, or taking up the space between the forward and backwards going current, and the Amperian contour should go around one of the currents?
I guess, but when we draw this, how do we know where to draw that flux surface? Like, how do we know how big to make it or small to make it, or is this usually defined in the problem?
In this case, the problem was to find the flux per unit length. So you, excuse me, I have to sneeze, I think. I hate it when that happens. I didn't actually sneeze. Okay.
Looking at something
So you
sometimes helps.
Oh, really?
It's a genetic
I should
thing.
try that. Yeah, that's so weird. So anyway, this flux surface needs to have a length, delta L. And later, when you're finding the flux per unit length, right? Flux per unit length is the flux you calculated divided by delta L, because that's what it means to be per unit length. And then you define this flux surface to go between the two currents. It needs to have one edge on one current and one edge on the other current. It needs to build the whole area of the circuit, except in this case, the circuit is sort of infinitely long, so we just do it per unit length. If you have a finite circuit, the flux surface is usually like, if we have a circuit that looks like that, the flux surface would literally be just the area of the circuit. It's whatever the current goes around. We have about 15 minutes left. And I still think a good thing to do here might be to do a Coulomb's law problem and an integrating charge density type stuff problem. Would that be helpful to people?
Sounds good to me.
Okay. Oh man, the sneeze reflex, that's wild. Okay. I actually want to do two separate problems because I want to do a specific type of Gauss's law problem. And then I will do a Coulomb's law problem separately because there's no way I would do this problem using Coulomb's law. Consider that we have a sphere. And within this sphere, we have a volume charge density that is making up an amount for the charge to be I'll just make it r cubed. And I want to know the electric flux density everywhere. How do I solve this problem? What do I do?
Derive an expression for the charge given the charge density function.
Okay, how do I do that?
Um,
Am I using Gauss's law?
I think so, because if you were to project an image onto the sphere, the magnitude of the electric field would be constant around that surface.
That makes sense. Yeah, what I like to think about it is if I took this problem and rotated it in some way, would it look the same? Clearly, it doesn't depend on any angle variables. If I had an observation point, though, and I moved it along r, it would not be the same problem. So I can tell my electric flux density is going to depend on r. But because there's so much symmetry going on here, it's pretty clear that I can do this as a Gauss's law problem. So yeah, the first thing I got to do is find the enclosed charge, which is what?
The density times the total radius.
Think carefully. What's going on here?
Sorry. Density times the area.
No, think again.
Well, as the area increases, you get more of the sphere, and the sphere contains it.
As the volume increases.
This is not a constant charge density, my friends.
Well,
Rho v times dv. Or sorry.
Yeah, you have to integrate it. Yeah. And we have to actually evaluate this integral too, because it's not constant here. So we can't just multiply by the volume of the sphere. That's the reason I gave you this problem. Now, I'm not going to actually evaluate that yet because we're trying to find the electric field flux density, everywhere, which means we would like to know it for values of r that are inside the sphere and for values of r that are outside the sphere. For values of r that are outside the sphere, there's only one value of the enclosed charge, which is the total charge in this thing. But for values of r that are inside the sphere, it's as though my Gaussian surface is a smaller sphere that's like only this big and has radius little r, right? So then I would only evaluate it up to whatever this radius is.
And that could be and we could also do it by making it, if we know Q total, it would kind of be a fraction of the Q total. If that's all we were given.
Yeah, you could do that if you knew the total Q and the distribution. You would really have to do the integral. Here's how we set it up. Let's figure out what dV is first. dV for a sphere is a thing that I think has thrown people off before. So I'm going to draw a diagram really carefully and see if I can clarify that. You could do it as a fraction of the sphere's volume only if the charge density was constant within the sphere. But since it varies within the sphere, the relationship between the volume of the smaller sphere inside the bigger sphere and the volume of the bigger sphere is not the same as the relationship between the charges they contain. Right? If I were to draw a graph versus R of the charge that is contained in this thing, it would go like this. So I couldn't just take like Q1 equals the total Q times V1 over V total. Can't do that.
It just clicked because like a lot of times
Yeah.
we have the density as it's just a constant number. It doesn't change, it's just sort of a property, but it's actually dependent upon the radius. It has a variable. So
Yeah.
it should have been a big clue to me, but
that it has a variable. Actually, yeah, that's a good thing everybody can check. When you see a charge distribution, check to see if it has a variable inside it. You know, if we just give you a constant, then it's a constant. But if it has variables, then that means you have to do the integral. So I'm going to define Q enclosed as a function of R. And that's going to be equal to, I'm going to change to an integration variable of R prime to keep me from getting confused. It's going to be rho V, so R prime cubed times dV. And now we got to figure out what is dV in this situation. So we have a sphere. I'm drawing a side view. So this is Z, this is X, and Y goes out that way, but I don't really care about Y right now. So let's just think about the cross section actually. We're going to need to multiply 3 different lengths together. If we vary something along R, we get a dr, right? So we're just going to have dr. That one's easy. If we move something along theta, remember theta is defined as down from the z-axis. So if we go along theta, this sweeps through an angle d theta, but again, angles don't have dimensions of length, and we need to know the arc length of this, so we have to add a multiple of r on the front. So far, so good. So we have dr times r d theta. Now, imagine we take this circle in the xz plane and we were to rotate it around the z-axis. That's kind of what phi is doing. Phi is rotating around the z-axis, but in a constant, at a constant value of z. Obviously, this distance is less than this distance, which is less than this distance, right? So if I were to take a slice of this radius, the slice of my sphere, the radius of this slice of my sphere is less than the total radius of the sphere. This value is theta. This value is r. So this length is, oh, I'm sorry, we're using little r, excuse me. This length is r sine theta. So now, That's my slice of the sphere that's parallel to the xy plane. It has radius r sine theta. What's this arc length? If I make this angle phi, that arc length is r sine theta d phi. And then I can multiply all these things together. R sine theta d phi goes up there. And this product of these three things becomes dV, the differential volume. So I took my sphere and let's see if I drew a sphere and tried to actually make it 3D. Here's my coordinate system. At a particular point here, I would have these sides are going along theta. These sides that are more horizontal looking are going along phi. And then I have to give it volume by going along r as well. And that's my little differential volume. It's really hard to draw this with a marker, but I hope you're able to see it. And different differential volumes at different positions on the sphere are going to have different orientations, as you can see. Because these are my circles of constant phi, and these are my circles of constant theta. Oh, all of these little r's need to be r prime because r prime is my variable of integration here. So now my new integral looks like r prime to the fifth, because I got another factor of r prime and another factor of r prime over there, sine theta d theta, well, I'm going to make these prime 2, d phi prime, d r prime. And the bounds on this for theta are 0 to pi, for phi are 0 to 2 pi, and for r prime, they are 0 to r, because remember, I'm trying to write the enclosed charge of a sphere of radius r that is some value less than the total radius of this thing. Let's name that A. Now we've evaluated this integral sine theta d phi multiple times. That gets you a factor of 4 pi. So that's 4 pi integral from 0 to r prime to the fifth dr prime. And that gets me 4 pi r prime to the, nope, just r to the sixth over 6. So that's the enclosed charge for values of r that are r less than or equal to a.
I guess I'm confusing why theta goes to, which one goes to pi and which one goes to 2 pi?
Theta is only 0 to pi because it's defined as the angle from the z-axis down like this. But you can go down this side just as easily as you can go down this side. And you can rotate all the way around in phi. So theta can only rotate down to the minus z-axis, but phi can rotate all the way around.
But didn't we draw it kind of backwards in this example?
To draw what backwards?
I thought we kind of defined it in the opposite way for this example.
No, I didn't do anything funny about the angle definitions.
Okay, so I'll just have to pay attention better. Okay.
Okay. Yeah, if you let theta vary all the way to 2 pi, you would be double counting because then you would be going all the way around this circle this way and all the way around the circle this way. And it would double count part of the sphere.
Yeah, I knew one of them had to be only to pi. I just wasn't sure which one we chose. So I guess
That makes sense.
I guess I'll look into conceptually
Okay.
into that.
Usually the convention is that it's theta. Okay. We only have a couple minutes left, but by looking at this problem and looking at the symmetry here, if I looked at an observation point here, I can see that like this differential charge element here would contribute an R-directed electric field. This differential charge element would contribute a field that's more like that. But this differential charge element would contribute one that's more like that. And their non-radial components would cancel, and that would also just only give you a radial component. So in general, we can say that your electric flux density has the form A hat R times some function of R. Now we can do Gauss's law, right? Because what we have to do is that flux integral d dot ds and set that equal to Q enclosed of R. ds here is just the RD theta. Oh, I see what happened. Yeah, that one should have been a, no, that one's a, it's like that. Yeah. Just the RD theta and the R sine theta d phi things multiplied by each other. So, and it's R directed. So A hat R d of R. So this d of R is an amplitude, and it has its direction vector external to it. And that's going to be dotted with A hat R, R squared, sine theta d phi. Evaluating all of this, nothing here depends on R. Like there's no integration along R, so these things that are R dependent can come out. This dot product evaluates to 1, and then again we're integrating sine theta d phi, which gives us 4 pi. So that is equal to 4 pi R squared d of R, whoops, down here, is equal to this thing that we got for the enclosed charge, 4 pi R to the 6th over 6. Moving some things around, divide through by 4 pi R squared. Boop, boop, boop. I guess the electric flux density inside this sphere is R to the 4th over 6. Outside the sphere, it would be different, and you would need to do this again because then the enclosed charge is constant. It would be A to the 6th over 6. And you would divide that by 4 pi R squared. And then you would have, or that would be A to the 6th over 6 times 4 pi R squared. That's what it would be outside. That is the amount of time that we have for today. As you know, I'm having my usual office hours today. On Thursday, I won't be able to have them because the Senior Design Expo Day overlaps with them, and I am attending that to support our seniors. I encourage you to also attend that if you have the time. Take a look at what those senior design projects are, because soon you'll be doing your own senior design projects, and also it's really fun to have sort of a department spirit of support between people. They'll feel good if you come watch them. I'll feel good if you come watch them, and you'll probably also feel good because then you'll get excited about what you get to do next year. So
Sorry, Professor, I apologize for cutting you off. Yes, what day and time is that? Does that occur?
It is tomorrow from 1:45 to 3:45 and
Okay.
Friday from 1:45 to 3:30.
Okay, all right, thank you.
I'm gonna type it in here. I see that it's not allowing you to submit homework 11. Yeah, that's because that's a manually graded homework and it's not one of the automatically resubmittable ones. So I'm only grading it once, which means it had a due date and it passed. That's the last day of our class, everybody. I want to thank you for being here and sort of bearing with me throughout all this weird remote learning stuff. I hope that you got it, and I appreciated everybody showing up and doing all these activities and being a good sport about everything. And I hope to see you next fall in some of my electives. I'll talk to you later. Don't forget to do your course evaluations.
Thanks, Professor. Have a nice summer.
Thank you. You too.
Sorry, one last thing about the exam. Is it,
Mhm.
so it's on all of the topics, all of the chapters in equal amount or around that? Or-
Yeah, expect kind of one problem in which you'll probably have to do an integral for each chapter-ish. Obviously, the transmission line ones, you can't do integrals about those. Those are not integral related, but like that level of complexity.
Okay.
It might take you half an hour per problem.
Okay.
They'll be like
thank you.
what we did today.
Well, thank you, Professor, and
You're welcome.
have a good summer.
You too.
Hi, Professor.
Hi.
Can I still submit homework 11? Because I didn't know the due date is past it.
Oh.
Yeah, I thought the due
that's
date is
fine.
like, yeah.
I'll reopen that homework and let you submit it until Friday.
Okay, thank you
Thank you.
very much.
I'm glad to hear you want to do it. And that one's about Smith charts, so I care about it a lot.
Yeah, I thought it's like at the end of the last date. That's why.
Yeah,
Missed-
most of them are, but that one I have to grade by hand, so I didn't make that one I didn't make that one available forever. Let's see. Okay, it'll be available until this Friday. Go for it. If anybody else had that problem, you can also submit it late or submit it until Friday. It won't be late. Anything else people need? Thank you. Have a good summer.
I guess if we have questions about the EM video, we could just email you them. I don't think I
Yeah.
will, but if I do it later.
Yeah, you can absolutely email them. And again, I'm having office hours today, so if you've got things to talk about, you can drop by then.
Okay. All right. Sorry, that was the final.
Okay.
Take care.
You too.